Hello everyone, I'm Masaya Mizutani from the University of Tokyo in Japan. Today, I would like to talk about our research, which is AutoMCM, Animal Coordination Service with abstracted functions for cooperative autonomous driving. Now, let's begin. These days, there are many researches related to autonomous driving. Right figure shows the architecture of AutoWare, open source software for autonomous driving. In the autonomous driving, there are several issues. For example, there are the problem of blind spot in the object detection process and the problem which overall optimal route planning is not possible in the planning process. Then, the cooperative autonomous driving is hot research area in order to solve these issues. This means that vehicles are connected and cooperate with each other to improve the safety and efficiency. Cooperative Intelligent Transport System, CITS, is one of the standardized systems of cooperative driving. CITS standardizes the network architecture, which is used for V2V communication, and right figure shows the architecture. Moreover, there are some standardized messages in CITS, such as CAM and CPM. These messages solve the issues of blind spots. On the other hand, there are some scenarios that CAM and CPM cannot solve. They include data, which is current position, direction, and speed of vehicles, but don't include future trajectory of vehicles. This means that it is not possible to take the future situation into account when the vehicles plan future trajectory. Right figure shows the situation that there are the obstacle forward and the yellow vehicle must change the lane. In this scenario, even though the blue vehicle can know the current position and the velocity of yellow vehicle, it cannot know that the yellow vehicle will change the lane. Therefore, the yellow vehicle must slow down the speed suddenly or stop in order to wait until the blue vehicle go away. Then, maneuver coordination message has been considered to solve this issue. MCM is still in the middle of being discussed and the format of it is not decided yet. Some researchers propose the MCM format, including vehicle trajectory, in order to cooperate planning the future trajectory of each vehicle. Then I introduced the Reddit work. There are several researchers that studied the maneuver coordination, and here I introduced the study of Lehman, which proposed the MCM being able to be used for several situations. In this study, they consider about the situation of this figure. The red vehicle is going to change the lane change and the future trajectory of red vehicle and the blue vehicle in the next lane is collide. Here, the red vehicle is called the prescriber and the blue vehicle is called the receiver. Then I explain the process of MCM. First, all vehicles send their own future trajectory periodically. Then the prescriber compares the trajectory of it and receiver and send the notification of collision detection to the receiver if detects the future collision. After that, the receiver decides whether it follows the message. If the receiver decides to follow, it sends the notification of permission and slow down in order to avoid collision. This enables the prescriber non-stop driving and makes traffic smoother. In this method, there are three problems. First, sending the message including trajectory data leads to increase the network consumption because the message including the trajectory is much bigger than the other messages. Second, it cannot correspond to the instruction duplication. In some cases, the message can be sent by multiple vehicles because all vehicles can send the message. Next figure shows that the red vehicle sends the instruction of deceleration to the blue vehicle, and then the yellow vehicle sends the instruction of acceleration to the blue vehicle. In this case, the last instruction overlaps the former one. This may cause the dangerous accident. Finally, it cannot correspond to the abnormal situation of the future trajectory change. Right figure shows that the red vehicle sends the instruction of deceleration to the blue vehicle because it will change the lane. But after a while, the red vehicle decided not to change the lane, so the blue vehicle don't need to decelerate. However, the blue vehicle must decelerate because it received the instruction. This is also one of the issues of the proposed method. So our study purpose of the our study proposed MCM meets several requirements to prototype the system and also integrate it into the autonomous driving software. Then we evaluate the effectiveness of proposed MCM in the specific situation. I explained the flow of proposed MCM in the scenario mentioned earlier. In this figure, the red vehicle prescriber will change the next lane and it will collide with the blue vehicle receiver. And arrows show the planned trajectory, which means the future trajectory of each vehicle. First, prescriber decides the lane change. Then the state turns to the advertising and the prescriber broadcasts the advertisement message periodically. When receiver received it, it replied the intention message, including planned trajectory of receiver to prescriber. When prescriber received the intention, prescriber replied the ACK message in order to confirm the arrival. Receiver continues to send the intention periodically until it received the ACK message. After a certain period, the state turns to the prescribing. If prescriber has received the intention, it distincts whether there are any risks of collision with the receiver. If there is a risk of collision, prescriber calculates the prescribed trajectory and send prescription to the receiver. When receiver receives the prescription, receiver verifies safety of prescribed trajectory. If receiver follows the prescription, it sends the acceptance message to prescriber. After that, receiver follows the prescribed trajectory until the prescribed trajectory finishes. They send CAM periodically. So if they cannot receive CAM of the another vehicle in a certain time, they decide as the communication error and finish the scenario in the way. Finally, at the end of prescribed trajectory, prescriber sends the fin message and scenario is done. Then I explain where the requirements are met. First, it can save network bandwidth consumption by introduction of advertisement message. Also, it can realize the reliable transmission by introduction of message. Second, it can correspond the instruction typification by introduction of statement. Finally, it can correspond to the abnormal situation or future trajectory change. This is because vehicles must send the cancel message at the abnormal situation, and when vehicle receives it, the vehicle returns to normal situation. From the above, this method meets all of the requirements. Next, I explain the system architecture of MCM. We designed the architecture that can be used for various situations, such as lane change, the intersection, and the lane merge. Therefore, we separate the function commonly required for maneuver coordination as MC service and the functions required individually as MC application in order to correspond to each scenario or application. Then I implemented the MC system for autonomous driving. We integrated two open source software, OpenC2X and AutoWare. This figure shows the architecture of our implementation. In this presentation, I don't explain the details because we don't have enough time. In our research, we prototype the system and run the test drive and evaluate it with planning simulator, which is installed as standard in the AutoWare. We did several tests and showed test driving them and the result of communication bandwidth and impact of MCM on traffic comfort. Also, we did the test drive in lane change scenario with 2 vehicles and 4 vehicles. This shows the visualization of the auto information with Rviz, which is installed as the standard in ROS. There are vehicles that change lanes prescriber, and 3 vehicles receiver ABC at the lane change destination. You can see that the prescriber selects receiver B in these receivers, and receiver B slows down in advance before the prescriber changes the lanes to get the proper distance. This figure shows the amount of communication at this time. The left is the case where only 2 vehicles are up-rated, and the right is the case where 4 vehicles are up-rated. For comparison, CAM is also transmitting at 10 Hz. Looking at this, you can see that the message containing trajectory is about 10 times larger than the CAM. Therefore, it can be seen that the bandwidth saving of this method is effective. Next, we investigated how much MCM impacts on traffic. We measured the time it took for the receiver to arrive at the destination about 260 meters ahead when traveling at 30 km/h and when traveling at 50 km/h. First, MCM, we can see that with MCM, we can see that the arrival time is reduced in both cases. Furthermore, the arrival time is shortened by about 5 seconds at 30 km/h and about 7 seconds at 50 km/h. It indicated that the faster the speed is, the greater the effect of MCM is. Finally, we measured the change in arrival time when the packet loss rate was changed. This time, we measured the arrival time at the timeout times of 0 second, 1 second, and 2 seconds. This graph classifies arrival time into 29 seconds or less, from 29 to 30 seconds, from 30 to 31 seconds, and 31 seconds or more. And we show them as the percentage. From the graph, you can see that the arrival time is increasing rapidly as the packet loss rate increases. It can be seen that the arrival time increases sharply from 10% at timeout time is 0 second, and 60% at timeout time is 1 second, and then 70% at timeout time is 2 seconds. Here, according to the study that conducted the practical evaluation of V2X, it was found that the packet loss rate was 20% or less in places where the obstacles such as walls did not enter. This result leads that this method has some robustness against packet loss when timeout time is 1 second or 2 seconds. Then I summarize this presentation. First, we proposed an MCM protocol that satisfies safety, facility, and so on. Then we implemented the MCM service, which was extended and integrated with AutoWare and OpenC2X. Then we tested Manabu coordination with multiple vehicles with a simulator and showed that it can be achieved. In addition, it showed that the bandwidth saving was effective and showed some robustness against packet loss. That's all. Thank you for listening.